Good morning, students. Now, today, welcome to all of you in lecture number 2 in optical fiber communication system. So, today's agenda is I will prove why optical fiber communication system has very large bandwidth, how optical fiber communication system supports very large frequency, and what is the spectra, in all the examinations and in all the interview. Sometimes they will ask the basic concept of the spectra, right? Frequency spectra and wavelength spectra. So what are the relation between them, I will explain today. And first thing I will explain here, in the last class I was given the concept about in optical fiber communication system. So transmitter, channel and receiver, right? So transmitter, channel and receiver. In all the communication system, as analog, digital, and any communication system, they are the basic three building blocks, right? Transmitter, channel and receivers. And in the last class, I also explained as far as the optical communication system, LED and laser source are the part of your transmitter, right? And what they do, electrical converted into optical, right? Electrical signal into optical signal. So here receiver pin, it's just summarized in the last class, and pin and APD, right? Pin and APD, and we will convert optical to electrical. So in channel is always optical. Now as far as the practical conditions, as an engineer, how you can know which signal is electrical signal, which signal is optical signal. So I am giving the some real-time scenario. You are able to see in the signaling, if you have done some internship in signaling sections in railways and BSNL, then you are able to easily detect, at the practically you can observe where is the electrical signal and where is the optical signal. So as an engineer, how you can see where the fault will appear, right? Where is the fault is appear, at the electrical signal or receiver part or the channel part. So always remember this. If the signal, I have no green color, otherwise if the signal is green color, if the signal is green color, then always remember that is the optical signal, right? Always remember in the life. If as an engineer, if anyone saw the spectra of the color coding, if the signal is green, then just observe that this is the optical signal. If the signal is blue, right, blue color, so that means that is the electrical signal. Always remember this, electrical signal, right? I have no green color, so I'm just change this color here, black. So when green color is there, please always understood that is the optical part, optical sections. If the blue color is there, then electrical signal is there. And if the signal is look like this, red signal, either that means some fault, or it is also known as reference signal, right? This is really important. So in last class I was given the some theoretical concept, and this is the practical concept. As an engineer, how you can identify which parts have the some some fault has been appeared in which side. So through, if the green color signal is just not glowing, that means the should be channel problem. If the blue part, blue sections have LED is not glowing, that means transmitter part will is the problem, or receiver part, after receiver part. But if the red is there is some default signals, or reference in the ledger. So this is the practical scenario. Always remember throughout your life, right? This is the basics of your optical communication system. Now, in today's class, I will first describe some the basic concept of the LED and laser. So someone maybe ask why LED and laser, right? So, and which one is better, right? LED or laser? So in your syllabus there is a separate sections of LED and laser. There is different chapters included in your syllabus. But today I just given some basic concept about the LED and laser. Since how you can differentiate and which one is a good one. So always remember that LED and laser can be explained through a spectral width. You can understood with this spectral width. See here, one spectral width is SW1 and this is SW2. Right? Now SW2 is greater than SW1. So basic concept related with the of LED and laser is directly related with the spectral width. If the spectral width is larger, so which communications? So always remember that. If the spectral width is larger, that means LED. And if the spectral width is lower, than laser. Why? Because in laser, the coherence phenomena is there, right? I will explain in the later phase. But in laser, the coherence phenomena is there and it behaves as an amplifier, right? But in the case of LED, no, there is no any coherence. Since conduction band, valence band, recombinations, right? So photon will be appeared and all the photons, right, are combined packets. No, energy E is equal to h mu. This E1 plus E2. E1 plus E2, so energy, packet energy. A packet of energy is known as photon, right? So photon release is diagonal in the case of this laser. All are coherent. So due to the coherence, the intensity will be high, but spectral width is low. And here the coherence is not phenomena is there, so all are different directions. So spectral width is larger. But practically, what will do? What are the things are related with this? Spectral width is hoga kya? What is the main advantage of the spectral width lower and higher? So see here, if the spectral width larger, let us assume that this one. So see here, this part is on, this part is off. This is again on, this is off, right? So here is 1, 0. 0 on, off means 0. See, so 1 0 you want to transmit 1 0 1 0. So how much time is required? This time, right? This time. See, but as far as this is the when the spectrum is larger than the LED, right, beta? Now see if when will this, so spectrum with this. So see, in the same time, you can able to see larger bit rate, right? On off. Here on off. So which one is on off time? In which case on off time is higher? So LED, right? LED on off time is higher as compared to laser. So now understood. If in digital communication system or in the current scenario, when we are looking for the very larger bandwidth, the data rate transmitted at this transmitter end, electrical signal is very higher. That is the pseudo dynamic sequence. This is also known as pseudo dynamic sequence. 1 0 1 0 1 0 1 0 1 0. So much high data rate is required. But here 1 0 1 0 1 0 like this. But here 1 0 1 0 1 0 1 0. So see which source will support higher bandwidth, higher data rate. So no doubt, this is the winner. higher data rate. What happened in this? What happened this? If forcefully I will tell no laser, please send the information 10101010. What happened? This should be lower, but naturally this should be shrink. So what will happen? So if you want to send the data information with high data rate with the LED, there is one very important. Please remember, always remember BVI. Then there is one function has been appeared that is known as peak overshoot phenomena. So that is the disadvantage with the LED. So the first concept, which one will support the highest data rate? Laser, no doubt. Laser is the winner. If LED we want to support high data rate, 101010, suppressed, compressed. So due to which your LED gone blast, and due to if you forcefully supports LED with a high data rate, your LED will blast, and that phenomena is known as peak overshoot. So this is known as peak overshoot phenomena in the LED. So the first concept, why LED and laser? LED and laser has the very good advantage. They will convert electrical signal to optical signal, no doubt, very good. But due to directional nature, coherence in nature, the spectral width is very low. So pseudo-dominant frequency can send with a very high data rate in the case of laser as compared to LED. LED has very big disadvantage. They have the larger spectral width. If you forcefully send the high data rates of data, then the peak overshoot phenomena is appeared in the LED. So what will do in LED? So yes, LED will support, no doubt. LED, where we will use the LED. So LED can be used in short range communications. So now the communication is two types. For the distance based communication. So short range communications and long range communications, right? So if short range communication, which source will be preferred? LED. And long range communication, laser, right? So this is the basic concept associated with the LED and laser, and that is simply, though I think you are able to understood the basic concept of this LED and laser, right? Now today in the last class, previously I told how much data rate or how much bandwidth will support the optical fiber. So in a joke I told infinite bandwidth, but how? No, practically infinite is not possible, but very large bandwidth. How that can support the very large bandwidth? So you know one formula: bandwidth is equal to operating frequency by Q, and Q is nothing but 50 or 100 will take, but it depends on frequency, right? So the concept is bandwidth is proportional to frequency, right? Frequency operations. So in optical fiber, if you will tell the bandwidth is very large, so it should be frequency should be larger frequency will support, right? Very larger bandwidth. In microwave, optical frequency is very large, very higher, right? Very higher, but not up to the optical fiber, because in terahertz, when we are going to the terahertz, gigahertz to terahertz, in that conditions, in microwave there is some disadvantage. What is this disadvantage? Since microwave component is the lump component, and if you will use very higher frequency, then some distributions phenomena will have some problem. Attenuation will increases, right? So microwave have as own disadvantage, but very higher frequency they will also show very high attenuations will show in the later phase. But now we will prove here how this bandwidth is very higher in the case of optical communication system. So here again I conclude some basic concept. You are able to understood why optical fiber communication system, why optical fiber is a backbone, what are the sources, so LED and laser, which one is better, where we can apply. So this is the basic combinations, and practically you can also identify where the electrical signal, blue signal, optical signal, green signal. If there is any fault or any reference signal, red signal. So just as an engineer, always this concept. Okay, any time in the life, if you are able to see this signal, by virtue this is this type of signals. You can able to detect any time, anywhere where the problem had been appeared, right? So I thought about some basic of this the basic journey of the optical fiber. Now I will prove the bandwidth is very larger in the case of optical fiber communications. So bandwidth should be proportional to your frequency. So now I will draw the basic spectra, and this is the electromagnetic spectra. And in the future, please remember, please don't always referred one by one. Sometimes I'm also in many times I was faced in an interview. I also forgotten what is the value of lambda, what is the value of frequency. So no doubt, sometime at that time, due to the time limit, we are not able to sketch the proper spectra, but very easy. So how we can see? So always remember that there are two type of relations. Lambda, if this is lambda, and here is the relation of frequency. So due to your observations, I will draw this with a different color, right? So this is the lambda and this is the frequency. What is the relation? So always remember that lambda is nothing but the relation with the lambda is equal to C by F. So inversely, right? Inversely proportional. Lambda is inversely proportional to the frequency. So here, so what I will do here, since I will plot this spectra for larger frequency, one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, कुछ भी कर लो. So now here 1, 2, 3, 4, same रखना, 5, 6, 7, 8, 9, 10 तक रखते हैं, बाद में कर लेंगे. Okay, so now see, lambda and f is inversely proportional, right? Lambda inversely proportional, right? So if lambda value is increases, frequency decreases. But here we are looking for the very high bandwidth, and already told bandwidth is proportional to frequency, right? तो मुझे क्या करना पड़ेगा? What will do? So wavelength decreases, frequency increases. Simple. So here in the first case, I will take the value is here. So let us assume that start 10 meter. 10 meter. Start करो बेटा. 10 meter. Divide by 10 meter. सबको 10 से डिवाइड करते जाओ. Divide by continuously. So 10 by 10 कितना हो जाएगा बेटा? 1 मीटर होगा बेटा. 10 मीटर के बाद हमने डिवाइड कर दिया 10 से, तो 1 मीटर. 1 मीटर इक्वल टू 100 सेंटीमीटर डिवाइड बाय 10 कितना हो जाएगा बेटा? 10 सेंटीमीटर होगा बेटा. सो 10 सेंटीमीटर. 10 सेंटीमीटर के बाद क्या होगा बेटा? 1 सेंटीमीटर, राइट. अब 1 सेंटीमीटर के बाद हमारे पास क्या आना चाहिए बेटा? 1 मिलीमीटर, फिर 0.1 मिलीमीटर और डॉट चलते जाइए. ठीक है. सो दिस इज द नथिंग. ऑलवेज रिमेंबर दैट दिस इज द रिलेशंस. कभी भी याद लाइफ में याद करने की जरूरत नहीं है. सो जस्ट रिमेंबर दिस वाले 10 मीटर से स्टार्ट करो एंड डिवाइड करते जाओ. एंड लैम्डा इज इक्वल टू इनवर्सली. सो नो डाउट इफ द wavelength decreases, frequency will increases, and here is nothing but this is the 30 megahertz. अब यहाँ पे 10 से डिवाइड किया है तो यहाँ पे क्या हो जाएगा बेटा 10 से मल्टीप्लाई, राइट। सो 30, उसके बाद क्या होगा, व्हाट इज नेक्स्ट, 300 मेगाहर्ट्ज। फिर क्या होगा बेटू, 3000 मेगाहर्ट्ज एंड लाइक दिस। सो 3000 मेगाहर्ट्ज, उसके बाद 3000 मेगाहर्ट्ज को आप क्या बोल सकते हैं, 3 गीगाहर्ट्ज, क्या हो जाएगा बेटा 30 गीगाहर्ट्ज, फिर हो जाएगा बेटा 300 गीगाहर्ट्ज, राइट। सो 300 गीगाहर्ट्ज, उसके बाद आप डायरेक्टली कर सकते हैं, लिख सकते हैं इसको 3 टेराहर्ट्ज, 30 टेराहर्ट्ज, 300 टेराहर्ट्ज, right? So this is a very very good concept about this. So now यहाँ के आगे लिख दो last 3000, right? So nothing. What we have done here? क्या value है? Nothing. Just remember this. If this lambda 10 meter, right? Divide by 10. Divide by 10. Divide by 10. And here multiplied by 10, right? So scaling. This is the scaling of the wavelength, and here is the expansion of the frequency. Now see. So I told bandwidth of optical fiber is very very higher because bandwidth is frequency directly proportional to frequency, right? If the Q is the constant 50 or 100, right? Now, so if I told in the first class very very larger bandwidth or infinite bandwidth, that means it should be here. It should be here. Who should be here? Optical fiber communications. So understood. So frequency support of optical fiber communication is here. So it's really really important. Now see here. कभी कभी भूल जाओगे कभी लाइव में, तो याद रखना up to here 3 गीगाहर्ट्ज, 3 गीगाहर्ट्ज से कम ही होता है, बट ठीक है, we'll see. This is the coaxial cable, and the middle of this up to 3 terahertz, or we are looking for also, but here this is a microwave communications, right? So life में कभी भी भूल जाना कि which communication we will apply. So always remember that. Just draw lambda is equal to 10 meter, divide by 10, 10, 10, 10, 10. Frequency 30, multiply by 10, 10, 10, 10. And here this is the coaxial cable, this is the microwave, this is the optical fiber. So optical fiber is up to 300 terahertz, 3000 terahertz. So what happened? So bandwidth is really what I told in the first class is right? That is infinite bandwidth. But how we can achieve this is really a challenging task, right? Because your fiber should be support of this frequency, right? This frequency. So how can support, which type of attenuation are there, what are the problems associated with the optical fiber in channel, we'll see in later phase one by one. But here I have proved that yes, optical fiber has very very larger bandwidth, and I think you people have no doubt regarding this, right? No doubt. So no doubt, microwave is very very good, very very larger bandwidth support, since we are looking for currently 5G, 6G, and beyond the different type of communications. Currently we are working on LTE advanced because due to the very very high frequency range, right? So this is the spectra. This spectra is really helpful for your future concern, right? Now one, the bandwidth. Second one, what are the other parameters is really important for optical communication system. So see here. Now since as per Shannon-Hartley law, you already know the capacity, right? Capacity is B log base 2 1 plus SNR, right? No doubt you are understood this concept. So channel is capacity is directly proportional to no doubt SNR. So second concept related with the optical fiber is SNR. SNR should be high. So signal to noise ratio, right? Signal to noise ratio. Sometimes SINR will also refer that is signal to noise plus interference. So I will deal later, but here signal to noise ratio is higher. Why? Why optical fiber has a better SNR as compared to coaxial cable and other communication system? Because optical fiber is affected very very low effects on the optical fiber, very low effects by your noise. Why? Since we know that in last class, in IoT class, I already told y is equal to is hx, plus your noise, right? If since here h is the channel coefficient, right? And channel coefficient. As for the wireless communication, this channel coefficient is h11, h12, and that can be is varied, right? Not constant, right? Varied, always varied due to the random nature. But as far as the optical fiber concerned, your channel is almost 1, right? Channel coefficient is almost 1, constant, right? Due to the wired nature, right? So due to the wired nature, bandwidth is very higher. Due to the higher bandwidth, some noise will not impact so much as compared to noise. See here, signal to noise. But here signal strength is very stronger because h is constant, so noise impact is very less, right? So as far as the second concept I will add here in optical communication system, first is what we will tell, large bandwidth, very large bandwidth. I will already proof. Second one is a large SNR. Large SNR. Why? Because noise is lesser and h is constant, right? Channel coefficient is constant. So this is the first one, this is the second one, and third one is also very important, that is known as attenuations. Attenuation. In optical fiber, attenuation is very lesser as compared to wireless and other media. Why? In the case of copper wire, twisted pair copper wire, electromagnetic induction is there. Some due to twisted nature, electromagnetic inductions are there, and other type of resistance are there in the wire. Coaxial wire is also the same. Attenuation is very higher. So how we can define the attenuation in the optical fiber? What do you mean by attenuations? Attenuation is nothing but this is the power reductions. Always remember that. Power reductions. What is the meaning of power reductions? Let us assume that if you want to send the information A to B, right? And here is some coaxial wire or optical fiber and anything. So if you want to send the information A to B, signal is this. So you will receive the signal this. See here, this is the amplitude A. This is represented to A dash. So A is very larger than A dash. What happened? This signal. Due to the attenuation in nature, the signal amplitude goes down. So why this happened? Due to the noise, some internal nature of the channel, dispersion, material loss, and different type of things can be happen. We'll discuss in later. But here we are basically discuss about only the attenuation currently. So what we'll do here, to send the information A, we require power P, but due to the reduction of due to the attenuation, power is reduced by 10 or P by 100 or P by 1000. What is the factor? So power, instead of power P, the power is now P by 10, P by 100, P by 1000. Why this 10, 100 and 1000? Because attenuation is always in terms of dB, right? So this is the power factor loss. So if 10 is 10 dB loss, right? Attenuation is 10 dB loss. If 20 dB loss, if 30 dB loss, if in the power factor, if 10 dB loss, 20 dB loss, 30 dB loss. So in loss in SNR is always represented in a dB, right? So how we can measure this factor? So see here, If always, this is really important, students. This is really important. If attenuation reduction by 10 dB, that means your power factor reduced by 10. If 20 dB loss, attenuation loss, then P by 100. See what is the factor. If 30 dB, then P by 1000. Right. So this is the attenuation is decreasing as per loss, attenuation loss. Right. So attenuation, how we can define attenuation loss is nothing but the power reductions. Which power? The signal transmissions power. Right. Signal power, signal transmissions. So less amount of power is now then transmitted with your signal towards the receiver end. Right. So this is the really big challenge of any communication system. So as far as the coaxial cable, twisted pair, and other media or wireless communications, attenuation is very large. But so what is the conclusion? Last conclusion of this class is low loss. Low loss. अब बेटा लॉस की बात करोगे तो क्या पढ़ोगे? लो attenuations, right? What are the attenuations? How this can be impacted in your communication system? We will discuss in the next class. Hopefully, we understood what the difference between LED and laser. Why laser is a better source as compared to LED for the long distance communications. At the same time, practically as an engineer, you can able to judge where the electrical signal, where the optical signal, where the reference signal you are able to see. And most important for any viva, anywhere, the spectra. I know every person's, and myself also, when I was in BTech, just remember this chart. No, please don't remember. Just lambda, just only remember this 10 meter divided by 10, here 30 and multiply by 30. And why bandwidth is very large in optical communication? Because bandwidth is directly proportional to frequency. And here we are able to see in optical communication, frequency support is up to 300 terahertz to 3000 terahertz. So thank you once again to all of you. I will continue this concept in lecture number 3. Thank you.